the application of piezoelectric sensors in structural health monitoring. It can be relating when we relate it to let's say the human health. So to diagnose if let's say a human is unhealthy, so what is the cause of unhealthiness, then in which body part is not functioning properly, and how to diagnose it, and what is the further treatment for that. So when we compare it to civil infrastructure, so the entire component of SHM, it can be categorized into 4 parts. The first is operational evaluation. So what are our objectives? What do we need to do in our SHM paradigm? Then is for that corresponding objectives, what data do we need? What type of sensors do we need to place? Where we need to place to obtain the corresponding data, which is most related to type of like health or type of feature we need to study about the structure's health. And next is feature extraction. So now we have got the data. So how to get the features which are most related to structure's performance or its health in its operational conditions. And the last part is how to discriminate between the features in various states of the structures, like in operational conditions, then in its severe condition or worse damage conditions. So how to discriminate between those features. So ideally, the entire concept of SHM can be categorized into 2 broad areas. First is sensing, and other is data analytics. So now, based on these sensing technologies, SHM can be categorized into 2 parts. That is local-based SHM and global techniques-based SHM. So when we talk about local SHM, it means when we are focusing on the member level monitoring. Let's say we have a frame structure of a building. We are focusing on particular column or a beam or slab of the structure. So we have multiple techniques like acoustic emission, then we have electromechanical imbalance technique, then we have ultrasonic waves, eddy current, and many more. And when we are considering the entire structure in a single go, we are monitoring the structure as a whole. Though that is called global monitoring, and static, global static, and global dynamic are such type of techniques. And global dynamic, which relates to model testing of the structure, is the most appropriate technique for global monitoring. And further, it can be further categorized into experimental and operational model analysis. So in experimental model analysis, we are able to measure the input provided to the structure, and in operational model analysis, we rely on its operational excitations. It can be due to pedestrian traffic, vehicular traffic, due to like micro tremors or the wind acting on the structure. So again, as I told in the last slide, so the component of model analysis, they can be categorized into excitation sources. They can be hammer shaker for experimental, and traffic movement, pedestrian motion, wind load, tremors for operational. Then again, sensing hardware, 2 types of most frequently measured parameters are acceleration and displacements and strains. So we can have accelerometers for getting the acceleration, then corresponding displacement model parameters from that. And we can have sensors such as strain gauges, fiber optic sensors, and piezoelectric sensors, which can measure static or dynamic strains. And the third part is data analytics, that is data extraction and processing and data discrimination to identify any change in the structure's health, and if change is there, then where it is and what is the severity of that change, and what are possible actions to be taken based on the data analytics. So again, when we talk about various sensing techniques, it is very important to discuss the sensor system, because the sensor systems compromises the majority of the funding required in a basic health monitoring system. It consists of sensing technologies, like that is sensors and data acquisition systems. So we have accelerometers, fiber optic sensors, strain gauges, and piezoelectric sensors, which are commonly used in both local as well as global monitoring techniques. So accelerometers, they are frequently used and most widely adopted as industry standard. Then fiber optic sensors, which are more sensitive and sophisticated, and they are more costlier also than even more than the basic accelerometers. So now piezoelectric sensors, they have a unique advantage compared to both of these frequently used sensors. They are very cost effectively, they are very sensitive, and they can work in both local as well as global monitoring techniques, which we'll discuss further. So let's discuss in brief about the piezoelectric sensors. So basically, piezoelectric sensors are smart material-based sensors which develop some kind of charge when external stress is applied to it, or vice versa. So if some kind of strain is applied on the piezoelectric material when it is bonded to some kind of host structure, corresponding voltage is developed due to dipole moments in the material, and that voltage can be further calibrated to get the corresponding strain in the structure. So it is very sensitive to measure the dynamic strain, but it cannot measure the static strain due to the involvement of the dipole moment changing in the material level. So there are two types of piezoelectric sensors based on their type of material. The first is ceramic, and that is polymer. The ceramics are more sensitive, but they are also more brittle. Polymer based piezoelectric sensors, they are a little less sensitive than ceramic, but they are also a little bit flexible, and they can be used in curved surfaces. So now, when we talk about the application in structural health monitoring, we begin from laboratory experiments. So first, we adopt a host structure that in this study, it was a pedestrian foot overbridge located near IIT Delhi. And we created a scaled-down model in laboratory for the in-depth experimentations. The scale was kept as 1:5. And we tested the piezoelectric sensors for their applicability in various types of excitations to capture the model parameters, then find out how sensitive are they to any damage occurring in the structure on the test structure itself. So we start by using artificial excitations through hammer. Then we have two shaker-based impact hammer-based excitations, and shaker-based random and shaker-based sweep excitations. Now, shaker-based random excitations, they were adopted since they mimic the actual random excitations occurring in the occurring on the bridge in its operational conditions. So these are the experimental details. The frequency range for the excitation was set from 10 to 500 hertz to capture the highest number of modes possible, and to see how the various types of modes in the low range or higher range are affecting the structure and how they are sensitive to damage scenarios. And the structure responses was captured by both accelerometers and strain piezoelectric sensors in the terms of acceleration and dynamic strain. Now, how to now we have covered the sensing part of the global monitoring. Now we come to the data analytics part. So in this, first we need to identify the structural parameters from the measured structure response. So it can be done in either the time domain or frequency domain. So there are various identification algorithms available, such as least square complex frequency or least square complex eigenvalue, or there are more advanced, such as enhanced frequency domain decomposition and stochastic subspace identification. So each method has their own advantage and disadvantage and their applicability based on type of excitation, then type of structure and all that. So in this study, we have adopted both the least square based method, that is least square complex eigenvalues for time domain, and least square complex frequency for frequency domain analysis. And we have compared how the identified model parameters vary from these two techniques. These are the stabilization charts from both the techniques from both the sensors. So in this chart, it seems congested, but it is easy to interpret. The blue lines or the blue dots corresponding to the modes which are identified but which are not stable, and the pink dots, they are they correspond to the stable modes. So now, how do we differentiate between stable and unstable modes? So that depends what criteria have been set before the identification. So we have, in terms of model parameters, we have model frequencies, we have damping ratios, we have mode shapes. So We can set a threshold for a mode to be stable if the difference between the particular mode in corresponding modal order is less than a specific percentage. And for this study, it was kept as 5%. So let's say two corresponding a single mode in two corresponding consecutive modal order, the difference is between less than 5%. It would be identified as a stable mode. So in that scenario, uh, the stabilization chart, they help us differentiate between the stable and unstable modes. Now, how to decide how many number of modes to acquire, or what is the frequency bandwidth we need to keep for these experiments? That entirely depends on our objectives. Ideally, for large-scale structures, initial 3 to 4 govern their overall response, and we can set the frequency bandwidth as per the requirement so that we can capture effectively the that initial 3 to 4 or maximum 5 modes. But in this scenario, the frequency range was kept up to, frequency bandwidth was kept up to 1600 hertz. So when we translate to the frequency domain from time domain, it means the maximum frequency bandwidth, that is 1600 hertz, give us good modes under the 800 hertz. That is the Nyquist theorem, that the maximum number of usable frequency is half of the frequency bandwidth adopted for the experiment. So now, based on that, we have converted the signals from time domain to frequency domain in the terms of FFTs, that is fast Fourier transforms, and we even identified the stable modes. Now, corresponding to these stable modes, we identify further modal frequencies, then damping ratio, and mode shapes. Now, these are the stabilization chart from impact hammer based excitation. This is from the shaker based random excitations. Now we can see there are multiple modes missing in shaker based excitations when we compare to this impact hammer based excitations. Now the reason behind this is that when we use impact hammer based excitations, we can measure the excitation, and then we obtain the corresponding FRFs, that is frequency response functions, which are basically the ratio of output in the frequency domain to the input in the frequency domain. So when we have, in that case, more number of modes are identifiable. But in the case of shaker-based random excitations, since excitations were set to random, and we adopted like unmeasurable excitations to replicate the operational conditions. And also, when we have input data in which force is not measured, we just get the response in terms of time domain signals. Now, those time domain signals are processed to get cross correlations in time domain itself, and they are converted to cross power spectral density frequency domain, and then they are fed as input to frequency domain algorithms. So it introduces some kind of process noise in that. So in that case, some modes the data gets like corrupted, and some modes are missed. And when we without any this transformation from time domain to frequency domain, we directly fed the cross correlations to the time domain identification algorithm. We get the modes like in quite good correlation to frequency domain algorithms. So it means when we have the raw data in the terms of frequency-based algorithms are better at identification, and when we have raw data in terms of time domain signals, time domain algorithms are better at identifying the modes. Now, the same scenario can be observed in the kind of shaker-based sweep excitations. Now, correlating the modal frequency and damping ratios from different excitations and different both the sensors from that is strain based and excitation based measurements. Talking about modal frequency, we can see that modal frequencies from all the 6 cases, that is under 3 different excitations and 2 different type of sensors, they are very well correlated, and we can see that they all overlap in the frequency domain plot, indicating a very good correlation between the frequencies. But that good correlation is not observed in the damping ratios. So because damping ratios, they have been observed to be very sensitive to the measurement type of excitation, then measurement technique, then type of sensors, then even the structural identification techniques. So given the changing of all the parameters from time domain signals to frequency domain, from acceleration to strain responses, from different then different type of excitation, that is impact hammer, then shaker based random excitation, then shaker based sweep excitations. So all of these parameters changing does not lead to a damping ratios be equivalent in all the cases. So this is a factor, one of the major factor that prohibits damping ratio to be used as a damage indicator in structural health monitoring. Now, when coming to mode shapes, so these are the first 10 mode shapes that we acquired, and the highest mode shape that was up to almost 400 hertz. So that is, if we are talking about the highest mode shapes of 400 hertz, we need at least the frequency bandwidth of 800 hertz. But in this experiment, it was kept up to 1600 hertz. That means we can get reliable data up to for the modes up to 800 hertz. Now, how to quantify the mode shapes from different excitations and different sensors? In that case, we use modal assurance criteria. It is basically a linear regression coefficient which tells us how two different mode shapes correlate. And it ranges from 0 to 1, indicating 0 for very poor correlation or no correlation at all, and 1 for excellent correlation, means 100% correlations. So these are the heat maps from different excitations with keeping impact hammer based modes as base as our reference modes, and comparing the mode shapes from shaker-based excitations to the impactor-based excitations from both the piezo sensor and accelerometer-based data. So we can see that the diagonal elements across all the heat maps, they show very good correlation with the amplitude in the range of 0.8 to 0.9. And this is acceptable correlation since the threshold which has been established in the literature for a good acceptable correlation is 0.75, and we are getting the values higher than 0.8. Now, these are cross-Comac values. These represent the correlation between the strain-based mode shapes and acceleration-based mode shapes under identical excitation. Again, the pattern is similar to what observed in the last slides in autocosmic values, that the corresponding diagonal elements, they show a very good correlation in the range, again in the range of 0.85 to 0.95, with 0.75 being the acceptable threshold. Now, an interesting point here is see that if we consider the average values of the mode shapes, or average MAC values of mode shapes, to relate how the initial modes and how the higher modes they differ in their correlation. It means how good the piezoelectric sensors are at capturing initial mode shapes or higher mode shapes, and we are more interested in the initial mode shapes since those govern the response of the structure. Those are more like they have more energy, and they contribute more to response of the structures. So in that case, we have divided the initial 6 modes in for the lower modes, initial 7 modes for the lower modes and higher 8 modes for higher modes. Now we can see the MAC values of the lower modes. They all in the average MAC values for all the cross MAC average cross MAC values, they are higher than 0.8, but the average cross MAC values, they are in the range of 0.72 to 0.76, indicating better correlation for lower modes than the higher modes. And again, the cross COMAC values, they are highest for shaker sweep based excitations, followed by impact hammer based excitations, and again by random based excitations, indicating shaker based sweep excitations, they are most effective at capturing good quality mode shapes. Now we have tested the efficacy of these piezoelectric sensors under artificial excitations which we can measure, and we chose some of them not to measure, like shear curve excitations. But when we talk about real life structures, it is very impractical and not feasible to use impact hammers or dynamic shakers to provide excitation to such large structures such as buildings or bridges. Even if we are capable to use shakers, we need very high amplitude shakers, and they further themselves changes the dynamic interaction of the bridge due to their heavy weight. So operational model analysis is the most feasible criteria or most feasible technique available for obtaining the model parameter of structure under its operational conditions. In operational model analysis, that is OMA, we generally use excitations provided by structure under its operational conditions. For example, in this model, scaled down model, the excitations were implemented through a human pedestrian walking over the scaled down model, and it was idealized in three different patterns. One was centric, when the to simulate the walking of the people over the bridge on the central line. Other was eccentric, over the walking over the exterior line, and third was haphazard. So it may be people running or people walking in different direction at different point of times. So the entire experimental regime and details were kept identical to the previous experiments. And we already discussed about the stabilization chart, so I omit that from this experiment. So now again, considering the few models of consideration both the sensors, we can now again impact hammer has been kept here as a reference excitation to compare the efficacy of piezoelectric sensors. In impact hammer has observed the best mode shapes and the highest number of modes in same frequency ratio, same frequency bandwidth. So compared to impact hammer, we can see that all the modes are identified at almost same frequency in both accelerometer and strain sensors. How some of the modes are missing in like eccentric or centric or random pedestrian motions. So now this could be due to the fact that when a person walks over the center line of the motion of the bridge or the model, so the bending when the bending mode shapes, they are excited better than the corresponding torsional mode shapes. Since the torsional mode shapes, they have a twisting or torsion pattern, torsion deformation pattern, and in that the opposite ends are under more deformation than the central line. But in bending case, the entire width of the span is under a same deformation in the bending mode shapes. So under eccentric pedestrian motion, torsion mode shapes are observed to be excited better, and centric mode shapes, bending mode shapes are excited to be better. And of all three mode shapes, random pedestrian motions, they perform best since they apply forces at all the nodes, be it at center or eccentric or any other node. So all the motion of the pedestrian is distributed all over the span. So again, these are the damping ratios obtained from all the three excitations along with impact hammer based excitations. So still we can see there is like variation is there in damping ratios from from both the sensors under even under a same type of excitation. So when we talk about eccentric excitation, both the sensors, we still see some kind of variation is there. Again, due to the possible aspect of different identification algorithm, different type of excitations, and different type of sensors. Now again, comparing the mode shapes from both the sensors under all the three type of excitations, we can see that the corresponding diagonal elements of these heat maps, they provide values in the again the range of 0.8 to 0.95, again indicating very good correlation. Now here the point to see is we have highest average Mach values for the lower modes in random pedestrian motions, and the higher the average Mach values from higher modes, so they are all comparable. But when we talk about the lower modes, which are of more importance, the random pedestrian motions, they give us better better relative mode shapes. Again, the reason is in random pedestrian motions, the force is applied at all of the nodes. It can be at center or eccentric based on the pattern of the pedestrian motion. Now, after establishing piezo sensors, very effective for model analysis under experiment, under artificial excitations, under operational excitations, it is important to see how sensitive are they to any damage monitoring. And since we cannot create any damage on the actual structure, we inflicted artificial damage on the scaled down model by cutting by introducing a vertical cut to the one third of the depth of the external member, as seen in this figure, we can see. Then introducing that vertical cut at 4 different locations, one close to boundary condition, then far from boundary condition, then 2 at centric position of the bridge. And then we also increase the severity of the damage by increasing the depth of the damage to 2/3 of the depth of the cross section. So overall, we have 8 different type of damage scenarios with 4 different locations and 2 different intensities. Now, since we want to test the efficacy of piezoelectric sensors for OMA in real life structures, so we obtain the excitation for this like damage monitoring to be random by distant motion, which was proved to be best out of all the operational based excitations in last study. So again, now all the measurement details were kept identical, and to now how to identify the damage from the measured model data. We have frequencies, we have damping ratios, and we have mode shapes. We have already ruled out damping as a very sensitive like parameter to any of the variation in the experimental details. So we rule it out, and we are left with frequency or mode shapes. Again, frequency is also sensitive to like temperature variations and boundary condition changes. So we also rule it out. So we are left with mode shapes. Now from mode shapes, there are multiple types of damage indicators that can be developed. One is MAC values. We have like studied earlier that. Then there we have COMAC values. Then we have strain energy methods. Then we have stiffness based methods and flexibility based methods. Now for this study, we have used COMAC based COMAC as a damage indicator. Now COMAC is an advanced version of MAC values. Now in MAC values, it give the MAC is an indicator for like relative regression of 2 mode shapes. It gives an overall indicator how close 2 mode shapes are. It does not cater to the variation at various measurement nodes. Like let's say we have 10 measurement nodes to create a mode shapes. So it would give us a single parameter by comparing all the nodes. But in COMAC, we get a relative relation between 2 mode shapes at every node, and we can even choose how many mode shapes are to be considered to get to that relative parameter. And again, the second damage indicator we use is flexibility based curvature. Now the benefit of using curvature is that it is being a higher derivative of strain or displacement. It is more sensitive to damage monitoring, and to obtain this curvature, we have to do double differentiative of acceleration with spatial derivative acceleration, and which can be directly obtained from single derivative of strain mode shapes. So again, it reduces the strain mode shape from piezoelectric sensors. They reduces the process noise in obtaining this curvature. Now, why flexibility based on curvature mode shapes, not stiffness? So as we can see from the basic formula for the flexibility, the convergence of flexibility based on mode shapes is dependent on few initial modes. And the initial modes, they are more important to study the dynamic behavior structure. So flexibility is a better alternative as compared to stiffness-based curvature for damage monitoring. So we have COMAC, and then we have flexibility-based damage monitoring, these two as damage indicators. Now, when we have these 2 damage indicators, further we take one step ahead in data analytics. We adopt Mahalanobis distance as the index to categorize whether the COMAC obtained at the particular node or the flexibility based curvature at particular node is damaged node or not. Now, basically, what Mahalanobis distance does is it gives us the distance of an observation from the entire group of observations. So, if we assume the damage node to be an outlier, which means the frequency, the curvature, or the Comac values of that particular node, they would lie outside the group of non-damaged elements. So it would have a higher Mahalanobis distance than the non-damaged elements, and we can identify it as damaged node or the location of the damage. Now, let's focus on frequency for damage monitoring. We can see that both the motor frequency for the 10 mode shapes under consideration and from both the sensors, they show negligible or very like low amplitude variation under different damage states. Now, these box plots, they show the average variation from all the nodes and all the damage states from both the sensors. We can see that across all the modes, the variation in the frequency is not like significant. So it cannot be effectively used to identify the damage. Similarly is the case for damping, although some kind of deviation is seen than damping, but no effective pattern can be established to identify the pattern of the damage or the location of the damage. Now, when we talk about our flexibility-based curvature as a damage indicator, and we have 8 different scenarios as I talked earlier. So now we can see that comparing the strain-based or curvature flexibility-based curvature from strain signals or from acceleration signals, they both are quite good at identifying in the initial damage. So now when we focus on the damage scenario 2, we can see that strain-based curvature values, they're higher than the corresponding displacement-based curvature values, which are obtained from displacement wave mode shapes. So this again establishes the piezoelectric sensors to be more sensitive to specifically initial damage. Now that is the important part, because we need to identify damage as early as possible in structure so we can monitor the progress of the damage. Although we can see that the displacement-based curvatures, they do not cross the threshold value at the damage locations 1, 2, and 3, even till the damage scenario 4. So, and the curvature-based values from strain-based signals, they already identify the damage from damage scenario 2. It means they are more sensitive to the damage compared to corresponding displacement-based values. So now we talk about Comac values. Now, when we see that the same pattern is observed from Comac-based values, but there is a significant difference. The dispersion of Comac values at non-damaged elements is negligible as compared to curvature-based values. In curvature, we had significant observable amplitude of curvature at non-damaged elements, but in Comac, the non-damaged element the values of Comacs are negligible. However, we see significant values at nodes corresponding to 15, 16, or 22, which are like in the adjacent to the nodes which have actual damage, like nodes 1, 2, 3, 4, and then again node 15, then 22 lies in the adjacent lane. And so it do have some kind of variation of signals, and again which is captured by the curvature of Comac values. But at all the other non-damaged elements, the variation of Comacs is insignificant as compared to variation in curvature-based values. Now we have established effectively in laboratory that piezo sensors, they are very effective at experimental model analysis, they're effective at operational model analysis, they're effective at damage monitoring, but still we need to test them in field. So for that, we went to the actual structure from which we fabricated the scaled down model. We pasted piezo disc buzzers at 8 different locations, and we monitored the dynamic chain-based signals. And we also actually place one accelerometer just to verify the modes which are identified the piezoelectric sensors. Although we have in-depth validated the efficacy of piezo sensors of capturing the modes in corresponding to accelerometers, but still we place one single accelerometer just to measure the frequency to validate the frequency of the modes, not the entire mode shapes. So again, the duration was kept like 1024 seconds, almost 15 minutes, and sampling rate was kept at 400 hertz with frequency relation 0.9 hertz. And now here, two other type of identification algorithm they were adopted, that is enhanced frequency domain decomposition and stochastic subspace identification. Now these two methods, they are proved to be robust in operational model analysis on real structures, since the amplitude of the signal of the response to be measured on actual structure is very less than which we have measured in laboratory-based specimen. So we changed the algorithms. We have placed 8 piezo sensors and 1 single accelerometers. Now, first we compare the modes identified from a single piezo and a single accelerometer. We can see that the first five modes, they were identified by piezoelectric sensors. However, the first mode, it was missed by the accelerometer. Now, this could be due to the frequency bandwidth of the acceleration in the working range. So higher the bandwidth of the acceleration, lower is its frequency resolution, which means it can miss out on some of the small peaks in if that peak does not lie in on the spectral line obtained from the data from accelerometers. Now, after establishing that we are good for the 4 or 5 modes, they have been equally obtained from piezo sensors and accelerometers. We further move on to obtaining the time domain data from 8 sensors, 8 piezoelectric sensors, which are now piezo disc buzzers. Now we again get the data from 8 sensors, and we apply both frequency domain decomposition and the stochastic identification to capture the modes. Now here again we can see that the first modes is missed by the time domain method, and it is captured by the frequency domain method. And again, if we see that this first mode 1.94 hertz is missed by both the single piezo sensors and single accelerometer. This could be due to fact that the placement of sensors at that particular place, which is not in the dominant deformation position in the first mode shape. So again, we have 6 mode shapes from frequency domain, and we have 5 modes from time domain identification. So these are the natural frequencies from all the domain, and we did 3 trial runs for measurements to just check the rapidity of our data. So we have 3 runs, and for the 3 runs we have 2 types of identification. One is frequency domain and one is time domain. So when we compare the data, we can see that the frequencies are obtained in very good correlation, but there is variation in damping ratio. Again, due to factors already discussed, variation in measurement duration or identification algorithms could be leading to this variation in damping ratios. So now these are the first 6 mode shapes identified by our piezo sensors of this bridge. First mode is again bending mode, second mode is torsion mode, third mode is bending plus torsion mode, fourth mode is again second bending mode, fifth mode is again torsion mode but is out of phase with the second mode, then sixth mode is again second bending mode with the torsion mode inclusive. Now we have from beginning, if we cover the entire gist, we have identified piezoelectric sensors to be effective in experimental mode analysis, to be effective in operational mode analysis, to be effective in damage monitoring in operational mode analysis, and they are effective in monitoring of actual real-life structures. But still, there is a lot of experimentation or a lot of validation to be done under varying environmental parameters, such as different type of loading, different type of temperature, and different type of pedestrian traffic during that like morning session, evening, or afternoons, because the variation of pedestrian loading also might affect the bridge behavior, and we need to further incorporate bridge pedestrian interaction models to further establish the performance of piezoelectric sensors. Now, these are the MAC values comparing the mode shapes from different runs, and we can see that almost identical uh, correlation is obtained with MAC values close to 1 from both EFDD and from different trial runs based on EFDD. And we are not talking here about stochastic identification because we missed the first mode in that. So we are capturing the MAC values for frequency domain decomposition only. Now, this leads to the application of piezo sensors in global monitoring. So when we talk about local monitoring, we know that piezoelectric sensors, they have been effectively used for many years using electromechanical impedance. But a major drawback using piezo sensors for both local and global monitoring is that we need to bond the sensors to the host structure. And specifically for global monitoring, to obtain a good mode shape, the mesh of sensors need to be like fine. So the more number of the sensors, the good resolution of the mode shapes, and more effective are the model parameters for damage monitoring. Or now in model analysis, it can the data acquisition can be done by two methods. The first is we can put sensors at all the location and we can excite the structures in one particular location. Or for small scale structures, we can put sensors at different location and we can just excite the structure, roam the sensors at all nodes individually, and we can excite the structure at a single point. And in EMI, we need to bond the sensors at all different locations to again create a fine mesh of sensors to effectively capture the damage. That increases the cost of the SHM paradigm or the entire cost of the project. So for towards that objective, we developed a magnet-based non-bonded configuration of piezo sensor. We tested it on the 2D plate structure for global monitoring as well as and damage monitoring. Global monitoring and local monitoring as well as using experimental model analysis and again electromechanical impedance. So this single conductance signature represent the reparability of the sensors. It was put on the structure, EMI signature was taken, then again it was put on the structure, removed and put on the structure, again the signature too was taken. So now comparing these two structures, we can see that we obtain a very high reparability of 99.7%. It means only deviation of 0.03% is there. 0.3% is there. Now, on this plate, two different type of damage scenarios were created, one near the boundary, one at the center of the plate, and in third damage state, both damage locations were created simultaneously. So damage state 1 correspond to removing the cover plate as shown in this figure at center of the plate. Damage state 2 correspond to removing the plate close to the boundary, and damage state 3 correspond to removing both the cover plates simultaneously. Then again, global monitoring was done through obtaining the curvature mode shapes, and local monitoring was done to obtaining the RMSD from every node at the plate using this magnetic piezo sensors. Now, when we compare both the curvature and RMSD values in all the damage scenarios, we can see that curvatures they are less susceptible or less significant at non-damaged elements compared to RMSD in all the three cases. And we can also see that both the curvature and RMSD, they're spread out to the elements adjacent to the actual damage location. So this might also lead to false damage detection if we are talking about significant threshold. If we are talking about without any significant threshold based on the data. So now how to reduce this dispersion of both the damage indexes at non-damage element? Now for that, we propose a hybrid damage index based on the combination of both RMSD and curvature. So for that, we have developed 5 different combinations. First is the linear combination, in which we linearly combine both the RMSD and curvature. Then we have multiplicative combination. Then if we have combination of square of the RMSD and curvature values. Now, when we compare these three correlations, we can see like these three combinations, they are tested on data from damage state 1 and damage state 2, and then the combined damage index, it is obtained, predicted for damage state 3 based on their values, and then again the actual damage state values, actual damage index values are compared with the predicted damage index values. So when we compare all these three combinations, linear, multiplicative, and square combination, we can see that square combination is very effective at reducing the noise at non-damage elements compared to other two elements. But the confidence interval of those HD, like the hybrid damage index, at specifically at non-damage element is very high. It means the confidence with which we can say that these are the HDI at the non-damage element is low compared to linear or multiplicative. But the confidence interval is very good in multiplicative combination compared to both linear or square. So we need to develop a combination of both square and multiplicative damage indices. So for that, we further develop two type of combination based on multiplicative and square indexes. The first is average of both multiplicative and square hybrid damage indexes. They are combined in the ratio of 0.5, and the weights are 0.5 for the both, and we can see that uh, the confidence interval compared to square is better, but it's not as good as multiplicative indexes individually. But in case of multiplicative square, in this we multiply the square of RMS, not just RMS in curvature, but we multiply the squares to the power of their weights. And we can see that the multiplicative square combination is best at predicting the combined damage index values, and they have very good confidence interval. They have the least reduced noise even compared to the square index values. So now this combined damage index based on local monitoring and global monitoring gives us a new effective damage index for robust damage monitoring and damage detection, with the measurement noise to be least or insignificant at non-damage elements. And how to quantify the performance of this model? So we compare the values from the predicted hybrid damage index values with the actual damage values, and we can see that the R square, that is coefficient determination, is almost 1, is equal to 1, and the root mean square error and the mean average error, they're 0, indicating almost 100% correlation. It means all the predicted values, they're almost equal, they're almost equal to the actual damage index, actual combined values. So this provides us a new hybrid damage index based on combination of both local monitoring using RMSD and global monitoring using curvature values. Further, we can adopt more number of damages states and more number of damage indices to create a further more robust damage monitoring index from by a combination of both local and monitoring techniques. Now we have seen that Piezo sensors, they are very good for local monitoring and global monitoring for both obtaining model parameters and obtaining damage through RMSD values. So now let's see a video which has been shot in the for the field application of Piezo sensors for the coursework at IIT Delhi. So let's go through this video.
Uh,
Uh,
so thank you, Dattar, for excellent presentation. Now we have floor open for questions.
yes, sir.
So just raise your hands if there are any questions, and we can take a couple of questions. It's already now close to 8 o'clock.
So I have a question.
Yes, please go ahead.
Okay. First of all, that a very interesting and very in-depth work. I really appreciate you for that.
Thank you, ma'am.
I don't know if it was all your part of PhD also, or if you are doing this at IIT Roorkee.
Ma'am, the last part,
Extended.
the data fusion part is I'm doing here, and the rest was my PhD work.
Wonderful, wonderful. Dattar, I just have my own doubts, not really from your presentation, but my doubts regarding this modal analysis thing.
Yes, ma'am.
When we are trying to capture the natural frequency in the field, if we have not done the numerical analysis of the structure, is there any way to get some idea that the results which we are getting are correct or not? Or maybe like you have been able to find almost like 3, 4 to 5 modes, but in real conditions, when we were trying it for the concrete structures, hardly first or maybe maximum second mode we could find. Or is there anything wrong we are doing?
Ma'am, the reason behind this could be that the concrete structures they are little more stiff than steel, which leads to a little bit less deformation. So
Mm-hmm.
data signatures there can be like captured in steel structures. Secondly, to differentiate between numerical modes or that like the data noise or actual modes, we need mode shapes for that because the when we see, let's say we have 8 sensors placed on the bridge, 4 along both directions. So when we have the actual modes which are correspond to the structural modes, they would be at the peaks in all the sensors, not just one sensor. But the peaks which correspond to the noise or the spurious numerical modes which are induced by data processing, they won't be there in all the sensors at same corresponding frequency data point. So we need mode shapes to differentiate between the numerical modes and actual modes, and there are like multiple indicators. We have moding and indicator functions, we have then complex frequency functions which tell us how strong a mode is to be actual mode or how like strong it's to be a spurious or numerical mode.
And these indices or analysis which you are telling, these are to be done in the post processing, or can we check it on the site itself while capturing the
So
data?
that depends what kind of software or what kind of deck we are using, but generally it's in
Mhm.
the post processing itself.
Okay, after you are with the data in your office.
Yeah.
Okay, and when we are talking about natural frequency, what we have studied is that it is only dependent upon the mass, stiffness, and the intrinsic properties of the structure, basically, and the span and the boundary conditions.
Yes, ma'am.
Do you also agree that it depends upon the load which is moving on the structure?
Yeah, ma'am. It the load moving on the structure do affect the frequency. See, the when external load is there on the bridge, be it moving or static, so it increases when we see the equation of a frequency, that is frequency
Mm-hmm.
directly proportional to stiffness and inversely proportional to mass. So the
Mm-hmm.
load increases the mass of the structure, which affects the frequency, but still
Okay.
like it does not affect that strongly compared to static mass. But still there is some kind of like if you're talking about a vehicular bridge, we
Mm-hmm.
have the phenomena vehicle bridge interaction, in which like some analytics is tools are there to differentiate the peaks corresponding to only the vehicle and the peaks corresponding to only
Okay.
the bridge frequencies, but the effect is there.
Like how much percentage it will change approximately? For
um,
example, if 5 hertz is the frequency I'm getting in the bridge, then what can I expect? 5.1 or 5.2, something like that? Not much, right?
yeah, ma'am. range of
approximately.
5.2, 5.3, but still the effect is there. But we can
Okay.
differentially effectively identify the peaks corresponding to vibration due to vehicle number of vehicles
Okay.
or the intrinsic property of the bridge itself.
Right, got that. Actually, I
Ah,
have now a data of almost 24 bridges for concrete bridges, and we should discuss this separately. How to do your use your skills on that data.
Yeah,
So
definitely.
we will discuss later separately. Thank
Yes.
you so much.
I would like to add
Sure,
that basically in bridges, it
sure.
depends on the live load and the mass of the bridge.
Mhm.
So usually the live load portion is very small as compared to the dead weight.
Yeah.
So mostly it gets absorbed, except
Mhm.
for very lightly loaded bridges where the vehicle weight may be significant.
Yeah,
This
that
is
was
one
a
thing,
yes,
the
sir.
effect of the mass. Other
Mm.
thing is that when the vehicles are moving, they have their own engine frequency. The not, engine frequency is high, but the vehicle induced frequencies. So they can also be separated out. But yes, if we are doing operational model analysis, then we have to live with some degree of
Mhm.
difference. We cannot
Okay,
be highly ideal that we get exact the frequency of the bridge.
Mhm.
So some portion will be there.
Okay. Mm. I got that, sir. Thank you.
Any other question by the audience?
Yes, sir. Good evening, sir.
Good evening.
Sir, thank you for the presentation. It was a very good presentation. I was fortunate enough to see it twice because we had once seen last year in our means in CIO 864 course also. Sir, I have some questions regarding PZT patch and some other things. Sir, what is the general design life we consider for a PZT patch? Means if it is bonded properly.
So it depends in like what configuration are we using. It is embedded. It has much greater service life, and if it's bonded on the exterior of the structure, it is like the bond. It depends on the bond life of the glue or the resin we are using. But still, like in our lab, we have sensors working like on surface bonded steps, like these sensors they are working over almost like 8 to 10 years. They are really working.
Not just 8 to 10 years. In fact, I have some
Yeah.
sensors. My oldest sensor right now working condition in the lab environment is as old as 2003.
Yeah.
Wow.
So 22 years.
Yes, sir.
Okay.
And in the embedded form, my sensor is working since 2008. Field, we install the sensors, but then we have not maintained the record.
Mhm.
So, but lab and our this condition there is no problem. The thing is that piezos we think that they are very low cost, so even if we have to replace, we don't mind installing a new sensor at the place. So, life point of view, because it's a very minuscule cost, so it's like we treat like consumable. Yeah, wires etc. They might be lost. So when we did the experiment at the Chicana Bridge, so after that some students were saying that let's leave the wires also. But I said, no, 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 let's bring the wires. And if we have to go next year, so we'll, reattach the wires. We have left the connectors. So next year we'll see. Next year, the next CVL 864 batch will come to know what happens in 1 year time. All the seven sensors, out of seven, six were working properly.
So we still have sir 8 sensors installed on that Panchil footover bridge. I think 2022, I guess.
Mhm.
We can even test that if they're working or not.
Yeah, that can also be done.
And sir, one question I have regarding the first mode, what we were missing in our piezo, single piezo and single accelerometer. Sir, it was a bending mode. 1.94 hertz. So why were we missing the first bending mode? Because it should be captured means wherever our sensor is placed. Means why was it missed, sir? I'm not able to comprehend it.
See, for the first bending modes, yeah, it's the easiest mode to capture, but still, if the sensor is placed near to the boundary condition or near to the support, the displacement would be very less. So, and effectively, the vibration induced by pedestrian in the operational condition is altogether the amplitude is very low compared to the excitation we provide in the lab scale structures. So, first, the excitation is very low. Second, if the sensor is placed close to the boundary. And third, when we talk about the frequency resolution of the data, so it might miss. There are multiple factors, but still, when we have a group of sensors, we effectively get that mode.
Okay. And sir, what damping ratio did we obtain in both the cases?
So damping ratio, I can show the plot. I don't remember the actual value, but the damping ratios vary from case to case.
Yes, because it was varying a lot because
Yeah,
in both the graphs there were so many means at places that data was at so many places. So means I was actually thinking that for steel structures we should get it around 2%. So are we getting the value what we usually take for our
value,
calculations?
the values are in the range, but still they are not consistent.
Mm-hmm.
I was shocked to see this much variation. Then I studied some literature. So it is like established pattern. Because damping ratios vary. If even we vary any of the one particular parameter to obtain the damping ratio, even its type of excitation, it may vary. Then even its type of measurement sensor, even in types of identification algorithms. So damping ratio are quite sensitive to all of these parameters.
And sir, one last question.
Sure.
Sir, we have basically done modal analysis with these sensors. So can we also perform some or create some stochastic model for vehicle bridge interaction? For example, in this case, there will be pedestrians or live load. So means can we have some model based on these sensors only? For example, we have used this for modal analysis so that we can know the variation of pedestrians throughout the day or throughout the season or means something like that. Can means do we have the data? If we have the data, can we arrive at some model? Then we can perhaps use it for some other analysis as well.
See, for a interaction model, we need the data from different aspects. First is we need the data from bridge alone. Then we need the data of bridge and pedestrian. Then again, we need the data with pedestrian alone. So we can get two types of data from the sensors on the bridge. That is bridge alone data, and then data with the bridge and pedestrians. But again, to get the data for pedestrian walking, we need a recent study conducted by UCD. They used the smartphones to capture the pedestrian motion data, and then they created a pedestrian bridge and pedestrian interaction model. Same they did with vehicle data and the bridge data to create interaction models between vehicle and bridge. So we need all three types of data to create effective interaction models. Again, that model would be effectively giving us the frequency peaks corresponding to the vehicular or the pedestrian motions, then peaks corresponding to the bridge, and basically they give us a range of the peaks which could be due to the bridge alone, and that could be due to the vehicular pedestrian alone.
Okay, okay, sir. What is the sir usual voltage range which we get in our when we are exciting our piezo? What is usually the voltage which we get?
The voltage is in the terms of like say 5 to 10 millivolts in the range of that.
Okay, sir. Okay. Thank you, sir. Thank you so much.
Okay, you're welcome.
So thank you everyone for joining. I think now it's 8:10, so it's dinner time for everyone. So
Yes.
thank you very much. So we meet in the next seminar next month.
Thank you, sir. Thank you for this opportunity.
We hold such talks every month, and if you want to join the Indian Structural Health Monitoring Society, you can just Google it, and you can just go to the website and fill up the application form. Thank you very much.